All right, hey everybody. In this video, we are going to be looking at skill 7. I realize actually there seems to be a typo here. Skills covered should probably be skill 7. Little smiley face. Love to start off a video with an error. In this video, we'll be talking about skill 7. This is numerical integration. And the idea behind this technique, or the idea behind this topic, is as follows. We've been learning a lot of different fun integration techniques that have really let us begin to take more and more challenging kinds of integrals, and that's fantastic. That's really great. However, there are certain integrals that will be either too challenging or straight up impossible for us to compute using the fundamental theorem of calculus. And let me clarify. There will be certain definite integrals that we might want to compute that we will not be able to compute by finding an antiderivative, right? In other words, there might be functions of the form or definite integrals of the form, the integral from a to b of f of x dx, in which we cannot find an antiderivative f, right? So we cannot find a function capital F that would allow us to use the fundamental theorem of calculus and calculate this as capital F of b minus capital F of a. There are certain little f's that are just too complicated for a nice formula for capital F to actually be present. So sometimes we cannot find a nice capital F. And that's really too bad. That's unfortunate. But that's okay, because the fundamental theorem of calculus is only one method that we can use to calculate definite integrals, at least to a high degree of precision. Remember, a definite integral always represents an area, right? Specifically a signed area between a and b of a function f of x. Signed area means that if it goes under the x-axis, then it counts negatively. As this function does not go under the x-axis, all of that would be positive area. But if this is our function f, the definite integral would just represent this area here. And you might recall, before we even learned the fundamental theorem of calculus, we were already looking at areas and figuring out ways to calculate that area, or at least approximate that area. And our favorite way to do this, either your favorite or least favorite, was using something called a Riemann sum, right? So as you might remember, a Riemann sum, let me actually zoom in here. A Riemann sum is something that we could calculate by creating a bunch of appropriately sized rectangles. All right, so we would specifically subdivide the interval a to b into a certain number of equally sized rectangles. We would calculate, I would say we would, draw the walls of these rectangles. And then we would calculate a certain height of the rectangles using an appropriate technique. Let's say the right endpoint of the interval itself, right? So here's my rectangle. I would just take the right endpoint and drag over, and that would represent the height of that rectangle. So here I would drag over, and that would represent the height. Drag over, and that would represent the height. And so on and so on. All right, what we get there is a bunch of rectangles, and we can use the area of these rectangles, right? So if I label these rectangles 1, 2, 3, 4, and 5, I could calculate the area of each of these 5 rectangles, sum up those areas, and get a pretty quick and easy approximation for the area under the curve, the actual area under the curve. And this was our Riemann sum method. Now, as a result, maybe I should say, in doing this, what we got was not the actual area. It was just an approximation. And you can sort of see that there's a lot of sort of extra white area, which I'm now coloring in as blue area. There's some extra blue area here that was not actually under the curve, but is inside the rectangle. So that's all being counted in our approximation. So what we end up with is not a perfect answer, but it's a close answer. And using a computer, it's really quick to compute, right? Because we can calculate length times width of rectangles really, really easily. And we can add those up really easily if we have a computer. Now, some quick words about this. We had a lot of notation to represent these things, and I want to briefly remind you of what that was. Each rectangle had a width to it, right? So each of these had a width. The width was specifically represented using the notation delta x. So the width was this triangle delta x. And the way that we calculated delta x, I'll sort of record this over here to the side. The way that we calculated delta x was we took the entire length of the interval from a to b, so that entire length b minus a, right? That's this entire area here. And then we just divided it by the number of rectangles that we were looking at, right? What I'll call n here. In this case, we were looking at 5 rectangles, so we would take b minus a, we would divide by 5, and that would give us the width of each of these rectangles. We were also interested in calculating the height of each of these rectangles. And the way that we calculated the heights, we used a similar strategy, but it gave us a height that varied from subinterval to subinterval. Specifically, we would take a given point in the little subinterval. So let's focus on this. Let's focus on this 4th rectangle here. I'll actually erase that circle. Let's focus on this 4th rectangle. What I did in the 4th rectangle is I chose some point in that 4th rectangle, and it happened to be the right edge of the 4th rectangle. I chose this point as my chosen value. So let me call that C sub 4. All right, or actually, I think to make sure that my notation is consistent for later in the thing, I'm going to call that x sub 4. And I'm going to call it x sub 4 star. But it's simply a chosen x value inside that interval. Specifically, in this case, it's the right endpoint of that 4th little subinterval. And then I would go ahead and I would plug that into the function. So when I say that I would go up and use that height at the function, what I really mean is that I'm calculating this height up here, and that height, or really, to draw the straight line across, so that this height, right, that height right there is f of x sub 4 star. And similarly, I would calculate the height of all the other rectangles, right? So this number right here, that would be x sub 1. This number here, that would be x sub 2. This number, that would be x sub 3. And I realize this is all getting really messy. X sub 4 we already talked about. And the far right endpoint would be x sub 5. Maybe stars on each of these. And we would need to calculate the various heights. So the height of the 1st rectangle, that would be f of x sub 1 star. And then ditto f of x sub 2 star, f of x sub 3 star, and f of x sub 5 star. So we would calculate all of these heights by taking our chosen x values and plugging them into the function itself. So we would have our widths. We would have all of our heights. Those are our f of x sub 1 star, 2 star, 3 star, and 4 star, and 5 star. So I guess I will call these x sub k star. And then we would multiply the height times the width to give us the area, and then we would sum all of those up. So our formula became a sum, and it was a sum over the number of rectangles. So we went from the 1st rectangle at k equals 1 to the 5th rectangle at k equals 5. And so we got this sum of f of x sub k star times delta x. And this was the formula for our Riemann sum. So the takeaway message here, the reason why I wanted to take us back and remember Riemann sums is that this gave us a way to get an approximate answer for our definite integral that used rectangles. And this gave us a way to estimate what that area was. Going forward, we are going to look at other estimations for area. And we are going to look at whether those estimations are good or bad estimates, right? So whether or not they're overestimates, underestimates, can we predict how good or bad they will be? And this is the world of numerical integration. So we'll start off class next time by diving into the so-called trapezoid rule and midpoint rule. And instead of creating Riemann sums, we will create, as you might expect, trapezoids and rectangles using interval midpoints. We will see how those are as far as, are they good estimates? Are they bad estimates? And we'll develop formulas to represent them. So it should be a good time. Again, it'll feel a little different than some of the other stuff we've done in class so far, but I think it should be fun. I will see you next time.